Stanley Yen actually is an expert, as you will hear, on neutrinos of every sort, having studied neutrinos from supernova explosions, neutrinos going through the Earth, neutrinos from the atmosphere. And he spent a lot of time in Japan, where they have beams of neutrinos going basically right through the islands and to the other side. And he comes by it naturally. He grew up in Sudbury. Many of you will know that Sudbury is where Sudbury Neutrino Observatory is located. So fortunately for him, he quickly moved from Sudbury to get his PhD at the University of Toronto, and then moved out to Vancouver, and has been living in Vancouver and working at TRIUMF, TRIUMF here, which is Canada's national accelerator, working in both nuclear physics, particle physics, and most recently a lot more on neutrino physics. So I met Stan when I myself went out there as a student in '83. I think he started in TRIUMF in '82. And so we've had a long overlap, I think more than most of you have been alive. So it's a real honor. Stan has been part of the outreach effort at TRIUMF as well, giving public lectures regularly. And this is a lecture that he's been giving across Canada. And if you ever get the chance to be in Vancouver, you should try and get a tour of TRIUMF. It's a fascinating facility. And they also have a morning lecture series, which is called Saturday Morning Lectures, which Stan also runs. And so it's my great pleasure to invite you to come up and tell us a little bit about the
Well, good evening, ladies and gentlemen. My name is Stanley Yen. Tonight I'll be telling you about several scientific mysteries, all of which are related to neutrinos, the ghost particles of the universe. I work at TRIUMF, which is Canada's National Laboratory for Particle and Nuclear Physics. This picture shows one of the large experimental halls at TRIUMF. And the background there, you can see our cyclotron particle accelerator. This picture also shows some of our 600 or so employees, of which I am one of the least. At TRIUMF, we build these wonderful particle detectors that allow us to track and measure the properties of subatomic particles. And we don't just build particle detectors for use at our lab, but we partner with various Canadian universities and institutes, and we send our particle detectors and our personnel and our expertise to many countries around the world to enable Canadian scientists to participate in international collaborations. And so in tonight's presentation, I will highlight some of the places where Canadian scientists have made global impact in the past and in the present and in the future. Now, my professional interest is in subatomic particles. My personal hobby is amateur astronomy. And so I'm going to combine these two interests of mine in today's lecture, and I will play the role of an astronomer who's going to use subatomic particles to find out more about objects in the universe. So now I'm going to dim the lights, and we will turn our eyes skyward, and we will start our journey into the cosmos. The first mystery is that of guest stars. At least 8 times in recorded human history, brilliant guest stars have suddenly appeared from nowhere. They typically become brighter than any other star in the sky. They persist for a few weeks or a couple of months, and then they slowly fade away, never to be seen again. One such guest star appeared in the constellation Taurus, just north of Orion, in the year 1054. And this was observed by, Chinese astronomers, and this star became so bright that it was visible in broad daylight for a couple of months before it began to fade away. This was recorded by Chinese astronomers in the Song Dynasty. You can see the star map here showing the position of this guest star. These are the astronomical records. And it says, since the 5th month of that last year, when the baleful star appeared, a full year has passed, and until now its brilliance has not faded. Its rapid movement, the variation in the length of its flaming rays, and the constellations on which it has trespassed excessively are a disapproving anomaly. It is greatly to be feared. This object was also seen by Native American observers in these petroglyphs in New Mexico. You can see a depiction of the guest star along with the crescent moon and the Pleiades star cluster. In the lower left, you can see Halley's Comet, which appeared about 12 years after the guest star appeared in 1054. This is what the sky would have looked like from New Mexico in August of 1054. And you can see the position of the guest star, the crescent moon, and the Pleiades. It's a very good reproduction of the position of those objects seen in that petroglyph. If you were to go far away from the city lights out to where the sky is dark, you can see thousands and thousands of stars. You can see the universe in all its grandeur. But when we look up at the sky with our eyes, we only look in visible light. Visible light is made up of the colors of the spectrum, red to violet. But just as there are frequencies of sound that a dog can hear, but which the human ear cannot hear, there are also wavelengths of light which the human eye cannot see. So if you look at the rainbow and you go rightwards from the red part of the spectrum, you can't see anything there, but there's actually energy there which carries information. And similarly, if you start at the violet part of the spectrum and you go to the left, again, you can't see anything there, but there is light energy there, which is carrying information. In fact, the visible spectrum, red to violet, is only a small slice of the total electromagnetic spectrum. You start from the red and you go towards the right, towards longer and longer wavelengths. You will first come to infrared, which is heat radiation. That's what triggers the motion sensors on your security lights. Then you come to the microwaves, which heat up the food in your microwave oven. Then you come to the FM and then the AM radio waves. You start from the violet part of the visible spectrum and you go to the left towards shorter and shorter wavelengths. You first come to the ultraviolet rays, which give you sunburn. Then you come to the X-rays, which the dentists use to X-ray your teeth. And at the very shortest wavelengths, you come to the gamma rays, which are used for cancer radiation therapy. And all of these different wavelengths of radiation can be used to look at the universe. So this is what the sky looks like in visible light. This is an all-sky map. You can see the Milky Way along the equator of this map. You can see it sprawling from horizon to horizon. You can see these dark lanes of dust in the disk of the Milky Way. You can see those bright white areas, which are clusters of stars that are shining brightly. You can see those pinkish clouds of hydrogen gas, which are lighting up like a big celestial neon sign. I'll draw your attention to that object there. That's the Large Magellanic Cloud. That is a satellite galaxy which is orbiting around our Milky Way galaxy. And I'll have more to say about this object later on in my lecture. So that's what the sky looks like in visible light. Look at the sky in infrared, it looks very different. So now we're looking at objects that are emitting heat, but not visible light. This is what the sky looks like in microwaves. The blue and white stuff near the equator is the dust in the Milky Way galaxy. But if you look towards the poles at the upper and lower ends, you'll see this sort of mottled pattern. That's the cosmic microwave background that's coming from outside our galaxy. And if you subtract away the foreground due to the dust in the Milky Way, this is what we'd see. So this is the famous cosmic microwave background. This is the remains of radiation from the Big Bang. And this is the distribution of energy in the universe 280,000 years after the Big Bang. So cosmologists look at this and can infer important parameters of the universe from this. If you look at radio waves, in particular at the 21 centimeter wavelength, you're tuning into hydrogen gas in the galaxy. So those blue areas are plumes of hydrogen gas in the Milky Way galaxy. You go in the other direction towards X-rays, that's what the sky looks like. See what the sky looks like in gamma rays. So in gamma rays, we're looking at very high energy processes in the universe, things like neutron stars merging together or material being sucked into massive black holes and being heated up so much that they shine in gamma rays. So you can see that each different wavelength of radiation gives you different information. This is an X-ray telescope in orbit. And on the right, you can see a picture of the X-ray emissions from a star that has exploded. So each one of those different colors represents a different wavelength of X-rays. And so those are coming from different elements. Each element emits a different set of X-rays. And those are the elements that have been expelled from this exploding star, and those atoms are being excited by the shock wave coming from that explosion. The left shows an infrared telescope, also in orbit. The center picture shows an object called the Eagle Nebula, M16, for those of you who are amateur astronomers. You can see these dark clouds of dust, nicknamed the Pillars of Creation, because this is a star-forming region. This is a region where new stars are condensing out of this cloud of gas and dust. In the center picture, which is taken in visible light, you can only see a few stars, but in an infrared, shown on the right, you can see a lot more stars. And that's because most of the stars here are still cocooned in the dust from which they were born. They're not emitting visible light because visible light can't penetrate the dust, but they're emitting infrared, and that's what the infrared telescope is picking up. So you can see it, you can get a lot more information from infrared than you can in visible radiation in this case. Similarly, if we look at the sun with an appropriate filter to protect your eyes, of course, in visible light, this is what you would see. You would see a few sunspots and not much else. But if you look at the sun at other wavelengths, in particular at the bottom row of pictures in the ultraviolet, you can see a lot of features that you don't see in visible light. That bright white spot below the equator is a solar flare. That's a material that's being ejected from the surface of the sun, and it's so hot that it's giving off ultraviolet radiation. So again, you see that by looking at different wavelengths, you get new information that you can't get by looking at the visible. In fact, when we're looking at the sun, we're really only looking at the surface of the sun. Light from the surface of the sun has to travel 150 million kilometers to reach us here on Earth, and at the speed of light, that takes 8 minutes and 20 seconds. When you look up at the sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes and 20 seconds ago. But that's not where the light really originates. The light and the energy that makes the sun shine actually come from the core of the sun, where the nuclear reactions are taking place. And the core of the sun is only 0.7 million kilometers below the surface. But light takes 20,000 years to go from the core of the sun out to the surface. So light's apparently going very slowly. And why is that? That's because the solar material is opaque to light and any sort of electromagnetic radiation. A particle of light that is made in the core of the sun from nuclear fusion only goes a fraction of a millimeter before it gets scattered by an atom that redirects that light into another direction, and then it goes another fraction of a millimeter before it gets scattered and redirected again. And so instead of making a straight line path from the core of the sun out to the surface, it makes this jagged, indirect, random walk And all that takes about 20,000 years on average before that light particle makes it up to the surface of the sun. So electromagnetic radiation of any type doesn't allow us to see what's happening in the sun today. If you wanted to look into the core of the sun, you would have to use some sort of radiation that goes in a straight line path from the sun to the observer's mind. It's like trying to take a picture of that person in the upper picture there. You want to take a picture of that person, the light rays have to make a straight line path from that person to the camera. But if you had a thick cloud of smoke between the person and the camera, then the rays of light would not be able to make a direct path. It would get scattered and redirected, and the more redirection you have, the fuzzier the image becomes, until eventually, if the cloud of smoke were thick enough, you get no image at all. So that's what it's like trying to look into the core of the sun using electromagnetic waves. Electromagnetic waves are one form of electromagnetism, which is one of the four fundamental forces in physics. Electromagnetism is very familiar to us. That's what allows us to see. That's what makes our computers and cell phones work. Another familiar force is that of gravity. Gravity is what holds us to the surface of the Earth and makes the moon go around the Earth and so on. The other two forces at the bottom there are not so familiar to us because these are short-range nuclear forces. They only operate when things get close enough to each other. By close enough, I mean like the distance of the diameter of an atomic nucleus. So there are two nuclear forces. The strong nuclear force is responsible for holding the protons and neutrons together inside the atomic nucleus. The weak nuclear force is responsible for radioactive decay. Now, the weak nuclear force is tens of millions of times weaker than the electromagnetic force. So now let me introduce the neutrino. The neutrino is a tiny particle with no electric charge. And since it has no electric charge, it does not feel the electromagnetic force, it only feels the weak nuclear force. And since the weak nuclear force is tens of millions of times weaker than the electromagnetic force, that means that the neutrino hardly interacts with matter at all. In fact, as we are sitting here in this theater tonight, every second, about 100 trillion neutrinos from the sun are passing through your body, whizzing through your body. You don't have to get alarmed about that. They're not doing you any harm because in your whole lifetime, only one of those neutrinos will score a hit on one of the atoms in your body. That's how weakly these neutrinos interact with matter. So it takes a lot of matter to stop a neutrino. So we normally think of X-rays as being a very penetrating type of radiation, and lead is a good material to stop nuclear radiation. If you take X-rays of the sort that your dentist uses, it would take a few millimeters thickness of lead to stop those X-rays. That's why when you go to the dentist's office, the dentist puts a lead apron around your body of a few millimeters thickness of lead to protect your body from those X-rays coming from the X-ray tube. You take gamma rays of the sort used in cancer radiation therapy, it would take a few centimeters of lead to stop those gamma rays. But if you wanted to stop a neutrino, you would need a thickness of lead of 400 light years. Now, 400 light years is how far light travels in 400 years. So, light goes from the sun to the Earth in 8.5 minutes. It goes from the Earth to the nearest star in 4 years. So 400 light years is 100 times the distance from here to the nearest star. You need a solid wall of lead that thick to stop a neutrino. And of course, there is no wall of lead 400 light years thick anywhere in the universe that we know of. And so that means that the sun, the Earth, the entire universe is practically transparent to neutrinos. So this is a sort of very penetrating radiation that we need to look deep inside astronomical objects. Well, what is a neutrino anyways? I remind you that an atom is made up of negatively charged electrons orbiting around the atomic nucleus in the center, and the atomic nucleus is made up of positively charged protons and neutrons which have no electric charge. Now, suppose that I took one of those electrons, which do have a negative charge, and I could somehow take away its negative charge. Well, that's what a neutrino is. A neutrino is an electron that's lost its negative charge. Well, how do you do that? Suppose that we had an electron and a proton, which were initially very far apart, but they're on a collision course. They're whizzing towards each other, and as they make a close encounter with each other, so that they're separated by less than the diameter of an atomic nucleus, the electron can sometimes donate its negative charge to the proton. And when it does that, the electron loses its negative charge and becomes a neutrino. And the proton gains that negative charge, and so the negative cancels out the positive, and that proton turns into a neutron. And so what comes out of that collision is a neutrino and a neutron. So let's look at that again. We have an electron approaching a proton, and then at its point of closest encounter, the electron donates its negative charge to the proton. The electron emerges as a neutrino, and the proton emerges as a neutron. So this sort of diagram is called a Feynman diagram, named after Richard Feynman, the physicist who first invented these diagrams. Now, electrons can lose their negative charge and turn into an electron neutrino, but electrons have heavier cousins. These are just they're negatively charged particles, just like the electron, except they're heavier. One of those is called the muon, another one is called the tau particle. We don't normally see these in everyday life because they're much heavier and they don't exist freely in nature, but we can produce these in large numbers in high energy particle collisions with a particle accelerator like the TRIUMF cyclotron. And in the same way that an electron can lose its negative charge and turn into an electron neutrino, the muon can lose negative charge and turn into a muon neutrino, and the tau can lose its negative charge and turn into a tau neutrino. So these are three different species of neutrinos that can exist. Particle physicists whimsically call this three different flavors of neutrinos. But if we're going to be talking about flavors, electron, muon, and tauon are just names, and I could give them a different name. For example, I could call these flavors strawberry, orange, and watermelon flavors. Okay, so for simplicity, for the rest of this lecture, I'll just call these strawberry, orange, and watermelon flavored neutrinos. Nuclear fusion in the sun occurs in the core of the sun where the temperature is about 15 million degrees. It's so hot that when hydrogen atoms collide together, 4 hydrogens can fuse together to make a helium atom, and as a byproduct, it produces electron-type neutrinos, or in my analogy, it makes strawberry-flavored neutrinos. And if this is true, if nuclear fusion is really what's producing energy in the sun, we ought to be able to detect these strawberry-flavored neutrinos with a neutrino detector here on Earth. So this is neutrino astronomy. We're going to use neutrinos as a way to find out what's happening inside astronomical bodies. So you can think about building a neutrino telescope to do that. And what are the requirements for a neutrino telescope? Well, first of all, it's going to have to be huge. Right? Something the size of the human body only intercepts 1 neutrino in your lifetime. And physicists are very patient people, but you want to gather a sizable number of events in a few years, so you're going to need many tons of material, a target for your neutrino detector. And secondly, you're going to have your neutrino telescope in a controlled environment away from any sort of interference. Neutrino signals are very faint and very rare, and if you try to detect neutrino signals here, let's say we placed a neutrino telescope in this hall here, you'd be trying to listen for the faint chirp of a cricket, like that. Normally you want to go to a nice quiet meadow on a morning. You'd be trying to listen to a cricket in the midst of this boisterous, noisy crowd here. Right? You couldn't hear a cricket in the midst of this crowd. And so that's what it's like trying to detect a neutrino here on the surface of the Earth. Because there's a lot of interference, lots of noise, this noise comes in the form of cosmic ray particles which rain down on the surface of the Earth. These are high energy cosmic rays that come from outer space, and they smash apart the top nuclei in the atmosphere and releases these subatomic particles called muons. These are the heavier cousins of the electron. And as we are sitting here, about 10 cosmic ray muons go whizzing through your body every second. You don't need to worry about it. It doesn't do you any harm. But if we had a neutrino detector right here in this hall, it would just lighten up with all these cosmic ray muons hitting it. So we have to put our neutrino telescope deep underground in a mine where you have 1 or 2 kilometers of rock to filter out all these charged cosmic rays. And the only thing that can survive are the neutrinos themselves. The first person to try to build a neutrino telescope was an American chemist by the name of Ray Davis. He worked in the Homestake mine in South Dakota, down in the mine 4,500 feet below ground level. His neutrino telescope consisted of a 6-meter diameter tank filled with 100,000 gallons of dry cleaning fluid. You can see the man there compared to this tank here. See that more clearly in the next picture. That's Professor Ray Davis on the scaffold there, looking down at his tank of dry cleaning fluid. The way this neutrino telescope works is, if the sun were really producing the strawberry flavored neutrinos that we expect it to, then of all the trillions and trillions of neutrinos per second streaming through this tank of dry cleaning fluid, about 39 times per month, one of those neutrinos would hit a chlorine atom in this tank of dry cleaning fluid, and it would make a nuclear transmutation and change that chlorine atom into a radioactive argon atom. Now, Ray Davis was an amazingly talented chemist who developed a way by which he could flush out this 39 atoms of radioactive argon from this huge tank of dry cleaning fluid, and he could isolate it and concentrate it and load this radioactive argon into a Geiger counter, and he could count the number of clicks that occurred when these radioactive argons decayed. That's how he counted the number of argon atoms that he had in his tank. Very daunting enterprise, sorting out 39 atoms of argon inside this huge tank. Trouble is, when he counted how many argon atoms he was getting, he wasn't getting 39 per month, he was getting about 13 per month, about only 1/3 as many as predicted. So when he first published this result, people just laughed at him and said, Ray, you just lost a few of your argon atoms. I mean, it's easy to lose 26 atoms in this huge tank of dry cleaning fluid, right? I mean, who you're trying to kid. But he showed that he actually didn't lose the argon atoms because he did test experiments where he injected a known amount of argon into his tank, and he was able to recover all of it. So it's not that he lost the atoms. And so this was the beginning of the mystery of the missing solar neutrinos. So that was a bit of a problem, but people didn't know whether or not they could believe this. And in science, a single experiment doesn't convince anybody. When we have a surprising result like that, people want verification by a different method. So another group built a different sort of neutrino telescope. This one is much bigger now. You can see the person standing there beside this neutrino telescope. This detector is called a Super-Kamiokande detector. It consists of faint flashes of light that are made when a neutrino hits one of the atoms inside this tank of water. You can see the person standing beside this huge tank here. Usually this tank is filled to the brim with water, but sometimes they have to drain the tank to do service work on these light sensors. This picture was taken when the tank was about half empty. You can see all these circular light sensors lining the walls of this tank. You can see the technicians floating around in this rubber boat. You can see cleaning the surface of these light sensors. Each one of those light sensors is about 20 inches in diameter. They cost about $25,000 US each. So you can imagine how much the 11,000 sensors in this tank cost the Japanese taxpayers. So when this group measured how many neutrinos were coming from the sun, they also counted only 1/3 as many as expected. So they verified Ray Davis's result. The solar neutrinos really were missing. And now people began to get worried because if nuclear fusion were taking place, then it should be producing the right number of neutrinos. And if nuclear fusion is not what's producing energy in the sun, then what could it be? So this is where, okay, one more thing. That neutrino detector I just showed you, that tank of water, has the advantage that it can detect which direction the neutrinos were coming from. So every time they observed a neutrino, it would compare its direction compared to the direction of the sun in the sky at that moment. And so they could plot its position relative to the sun's position, and that's what's done in this picture here. This thing is acting like a neutrino camera. So the sun's position is at the center of this picture, and the colors there represent the intensity of the neutrinos coming from that direction. You can clearly see that the center is where this picture is the brightest. Most of the neutrinos are coming from the direction of the sun. So this thing is acting like a neutrino camera. This is really a picture of the sun taken using neutrino radiation. A real neutrino telescope here. So now we still have the problem about why the solar neutrinos are missing. And this is where Canada and Queens comes to the rescue, because a team of Canadian, American, and British scientists, and Queen's University was the lead institution on this. This group built another sort of neutrino telescope called the Sudbury Neutrino Observatory. This consisted of an 18-meter diameter acrylic flask located in a mine in Sudbury, 2 kilometers below the surface. This is an experiment that only Canada can build, because this acrylic vessel is filled with about 1,000 tons of heavy water. Heavy water is what's used in CANDU nuclear reactors. And only Canada sells CANDU nuclear reactors. So only Canada had the huge stockpile of heavy water that was required for this neutrino telescope. So this team of physicists borrowed $200 million worth of heavy water from Atomic Energy of Canada and shipped it to Sudbury and brought it all underground into the mine and filled this huge acrylic vessel with heavy water. This picture shows this acrylic vessel. You can see the size of it. There are some people standing on that railing down at the bottom there. You can also see some of the 9,000 or so light sensors that are used to pick up the faint flashes of light when a neutrino hits an atom inside this tank of heavy water. And now, when this neutrino telescope counted how many neutrinos it was observing, it observed the number that you would expect if nuclear fusion were producing energy in the sun. Okay, so this is the solution to the puzzle of the missing solar neutrinos. They are really not missing at all. So why did the Sudbury detector, which used heavy water, count the proper number of neutrinos, whereas the Japanese detector with water and the American detector with dry cleaning fluid counted only 1/3 as many? It's a matter of flavor sensitivity. Heavy water is sensitive to all different flavors of neutrinos. It's like sticking out a tongue which has taste buds that can taste strawberry, orange, and watermelon. Whereas the other two detectors are not sensitive to all flavors, they're only sensitive to strawberry flavors. It's like a tongue that only tastes strawberry. And so what's happening is that as these strawberry flavored neutrinos are introduced in the core of this sign, on their way to the Earth, they're changing into orange and watermelon flavored neutrinos. So if your tongue only has taste buds for strawberry, you're missing 2/3 of them. And that's what's happening. So this phenomenon of changing from one neutrino flavor to another is called neutrino oscillations. And this can happen only if neutrinos have a small mass. So prior to this point, physicists thought that neutrinos had zero mass, just like particles of light or photons. An observation of neutrino oscillations showed that neutrinos must have a non-zero mass. Well, we've seen that strawberry-flavored neutrinos in the sun can turn into orange and watermelon. Does it work the other way around too? What if you started with strawberry or started with orange-flavored neutrinos? Can they change into strawberry neutrinos? To test that, an experiment was mounted in Japan called the T2K experiment. Although this was located in Japan, Canadian physicists played a pivotal role in conceiving this experiment and designing the apparatus and carrying out this experiment. In this experiment, a circular particle accelerator at J Park on the east coast of Japan, just north of Tokyo, was used to produce a beam of orange-flavored neutrinos. And they fired this beam of orange-flavored neutrinos at that big water tank, Super-Kamiokande, which is located near the west coast of Japan. And it was observed that as these initially orange-flavored neutrinos were flying the 295 kilometers over to the west coast of Japan, some of them changed into strawberry-flavored neutrinos. So indeed, orange-flavored neutrinos can also change into strawberry flavor. In 2015, Queen's own Professor Arthur MacDonald shared the Nobel Prize with Professor Kajita of the University of Tokyo for the discovery of neutrino oscillations, which shows that neutrinos have mass. It's a very proud day for Canada and for Queen's University. So Canadian physicists are having global impact. This is not the first Nobel Prize for neutrino research. In 2002, Ray Davis, who built that dry cleaning fluid detector, shared the Nobel Prize with Professor Kashiba for pioneering contributions to astrophysics, in particular for the detection of cosmic neutrinos. So back to the mystery of the guest stars. In 1054, there were no other types of telescopes available. Astronomers just looked at this thing with their eyes, and they could only observe in visible light. But using the tools of modern astronomy, we know a lot more about this. This was actually a supernova explosion. So now when we look at that part of the sky, modern astronomical telescope, this is what you would see. You would see this object called the Crab Nebula, M1 for those of you who are amateur astronomers. So in a sufficiently large telescope, you would see this as a big expanding cloud of gas which contains all the elements that were expelled from this supernova. Here's another image of a supernova. This one's in a galaxy outside the Milky Way galaxy. You can see the host galaxy here. Right there is the new star. So if this photograph had been taken 2 days earlier, there would have been no star at this position. And you can see that that one star is practically as bright as the entire host galaxy, which has 100 billion stars in it. So it's already a spectacular object in an astronomical telescope. But if you had eyes that could see in neutrinos, that supernova would look 10,000 times brighter than this. A supernova explosion produces 99% of its energy in the form of neutrinos, only 0.01% of it in the form of visible light. We now know that a supernova, a core collapse supernova, is the end of the life of a massive star. So if you think about the lifeline for a 25 solar mass star, it would burn hydrogen for about 7 million years, would burn helium for about 500,000 years, would burn carbon for 600 years, neon for 1 year, silicon for 1 day, and then when it builds up a sizable iron core in the center, nuclear burning stops. Because iron is the most stable nucleus that there is. Whether you make iron undergo nuclear fusion or nuclear fission, you can't get any more energy out. And so at that point, there is no more energy coming from the center of this star. There's nothing to hold the star up against the pull of gravity. And if that iron core is massive enough, it will undergo gravitational collapse. So to explain to you what that means, just remind you, here is an atom with the electrons orbiting around the atomic nucleus. Actually, this greatly exaggerates the size of the atomic nucleus. It's much smaller than this. In fact, if you could magnify an atom to be the size of this football stadium, the atomic nucleus would be about the size of a cherry at the center of this stadium. Most of the volume of the atom is taken up by the electrons. I remind you of this Feynman diagram where an electron can make a close encounter with a proton. The electron donates its negative charge to the proton and turns into a neutrino, and the proton turns into a neutron. So that's what's happening in this iron core. The density is so high that the electrons in those iron atoms can make close encounters with the protons in those iron nuclei. Those protons get turned into neutrons, and the electrons emerge with a flash of neutrinos coming from that collapsing iron core. And so you remove all the electrons, which remember take up most of the volume of an atom, so that football stadium shrinks down into the cherry, and that iron core, which used to be about the size of the Earth, shrinks down into a sphere of neutrons about 20 kilometers in diameter. A neutron star actually quite a small object. So in this picture, someone imagine what it would be like if you could suspend a neutron star above downtown Vancouver, and that's what it would look like. Now this stuff, remember, weighs as much as 1.5 solar masses. It's only 20 kilometers in diameter. And so this stuff is incredibly dense. If you could take a teaspoon, you could scoop out a teaspoonful of this neutron star material, it would weigh about 500 million tons. Now that stars are typically rotating around. So when that iron core, which was slowly spinning around, collapses down into that cherry, that's something like a figure skater who pulls in her mark. She speeds up her spin tremendously. And so it has been observed that at the center of the Crab Nebula, there is a star that blinks on and off about 30 times a second. That's the rotating neutron star, which is beaming out a beam of radiation. And because it's rotating around 30 times a second, that's like a searchlight that swoops around and intercepts the Earth 30 times a second. So it's incredible that this thing, which weighs 1.5 solar masses, is spinning around at 30 times per second. Physicists and astronomers have been trying to model what happens inside a core collapse supernova for about 30 years. They can't actually see what's inside, so they make computer models. And so what happens is that that iron core shrinks down into a neutron star that leaves a void, and all the stuff lying on top of this iron core then collapses inwards if there's a void, and it hits this very incompressible neutron star, and then the shock wave propagates back outwards, and you would expect the star to explode, but in your computer models, the shock wave just becomes weaker and weaker as it's pushing against all this material falling in. And what they find in your computer models was that the shock wave eventually stalls and the star does not explode. And so that was a mystery for about 30 years. They couldn't get their supernova models to explode. And eventually it was realized that they were missing something, namely the neutrinos. Initially, people thought neutrinos just go through everything, right? And they have no effect on the supernova explosion. But that's actually not true, because there are so many neutrinos that even if a small fraction of them hits an atom on their way out and dump their energy into this envelope of material around the neutron star, that's enough to heat it up so that the shock wave is revived, and that's what makes the star explode. So if it weren't for all these neutrinos coming from this neutron star, supernovae would not explode, and we wouldn't have any guest stars to look at and talk about tonight. It takes many months of CPU time on supercomputers to model what's happening in this very complicated environment. On the left, you can see an animation made by a group in Germany. So this is just tracking the first 1 second or so of this supernova explosion. You can see that as the neutrinos are streaming through, it's heating up this material, and that material is violently vibrating back and forth. Those oscillations get more and more violent as this stuff gets heated up by the neutrinos. And eventually, the oscillations become so violent, you get these hydrodynamic instabilities, and that's when the star explodes. It's like taking a kettle of water, and as you heat it up, it's getting closer and closer to the boiling point, and the stuff bubbling and bubbling more violently. Now, if you were to look at this object using an optical telescope or any sort of electromagnetic radiation, you would see nothing, because the star is opaque to electromagnetic radiation. But in the next generation of neutrino telescopes, you'll be able to see the neutrino intensity going up and down. You can see that here, up and down on a millisecond time scale as this stuff is sloshing back and forth inside the core of that star that's about to explode. So to observe a supernova, we would ideally like to detect it early, and neutrinos allow you to do that because the neutrino signal comes out promptly, whereas the light takes some hours before it makes it out to the surface of the star. A neutrino telescope is always watching. You don't have to wait for nighttime because the Earth is transparent to neutrinos, and it's pointing in every direction at once. So a neutrino telescope is the ideal way to look for a supernova that's about to explode. I'll remind you of this picture. Remember, this is the Milky Way. There's a large Magellanic Cloud. That satellite galaxy. That's an enlargement of it. On February 24, 1987, a supernova exploded in the Large Magellanic Cloud. So the left shows what it was like before the explosion, and on the right is during the explosion. Now, this object was discovered visually by a Canadian astronomer working at an observatory in Chile. He saw something funny on the photographic plate that he was taking, so he stepped outside and looked up at the stars, and he looked at the Magellanic Cloud and said, "Hey, that has a star in it that wasn't there before." So this supernova was discovered in optical wavelengths. It so happened that there were 3 neutrino detectors in operation on the Earth at that time. They weren't specifically looking for neutrinos, rather they were trying to study other problems in particle physics. But after the supernova was observed visually, they went back to their data tapes and replayed them, And they realized that at the time of the supernova, there was a burst of neutrinos in their neutrino detector. So it looks something like this. Right at the time of the supernova, you can see a big spike of neutrinos. There were a total of 23 neutrinos detected. Nowadays, we have much larger neutrino telescopes. The world's largest is this telescope called IceCube, which is located at the South Pole. In this neutrino telescope, very enterprising physicists go to the South Pole during the Antarctic summer when it's relatively warm. They have to ship tankers full of diesel fuel, which they burn to melt the ice and make jets of superheated water that they use to drill these boreholes vertically into the Antarctic ice cap, down to a depth of 2.5 kilometers. And then when these boreholes are filled with this liquid water, they drop in strings of light sensors that they allow to freeze into position. And the way this thing works is if a neutrino were to hit an atom inside this 1 cubic kilometer of Antarctic ice, it would make a flash of light which is picked up by these light sensors. This picture shows one of these boreholes. They're about 18 inches in diameter. This one's filled with liquid water, and you can see them dropping in this string of light sensors. In July of 2018, last year, this detector was in the news because it detected one very high energy neutrino, and at the very same time, a gamma ray telescope that was in orbit picked up a flash of gamma rays coming from a distant galaxy. So this was interpreted as being from what is called a blazar. This is a supermassive black hole that is sucking in material and heating it up so that it emits gamma rays. Those gamma rays are energetic enough that they can produce other particles that can decay into neutrinos. So this is an example of what is called multi-messenger astronomy. This is where you look at the same object using neutrinos, using gravitational wave detectors, using different wavelengths of electromagnetic radiation, each one of which gives you different information about this object. This is what the sky looks like in visible light. This was what the sky looks like in neutrinos as observed by the IceCube detector. So it looks very different. My very small contribution to this field of neutrino astronomy is in the effort that I and my colleagues put into building this thing called HALO, which is an acronym for Helium and Lead Observatory. This is a neutrino telescope which is located in that mine in Sudbury that I talked about earlier, just a different part of the mine than the Sudbury Neutrino Observatory. We built this completely out of surplus materials. We inherited 80 tons of surplus lead, and then we got neutron detectors from another experiment. And so we built this $6 million experiment for a couple of $100,000. The taxpayers got a real bargain. In this neutrino detector, okay, this is located in this physics lab called SNEWS lab in the Creighton mine in Sudbury. Queen's University is the lead institution for SNEWS labs. We can be very proud of that. You have to go down this elevator shaft down to 2 kilometers underground at 6,800 foot level. That's the height of the CN Tower by comparison. So it's like 5 CN Towers underground. And then when you go down to the 6,800 foot level, you have to walk horizontally about 1 kilometer to get to the physics lab. And so you're walking through a dirty mine. You have to wear a miner's helmet and a headlamp, and it's dirty and muddy in there. And then when you get to the entrance of the physics lab, you have to get rid of all this dirt. So you have to shower, you have to take off all your mining clothes, you have to shower and then put on clean room clothes. So here we are, 2 kilometers underground. That's me on the left, and a student and a technician, were hoisting in these rings of lead, which weigh about 85 kilograms each, about 800 of them, and we're just piling them on one at a time to build up this neutrino detector. Our detector consists of rings of lead shown in gray. At the center of these rings of lead, we have Geiger counters that are filled with this very rare helium-3 gas. So that's the main cost of this detector. Unfortunately, we didn't have to pay for it. And the way this thing works is, if neutrinos from a supernova in our galaxy were to hit the lead, it would knock out a neutron from the lead nucleus, and this neutron would bounce around inside the lead for about 100 milliseconds, 100 microseconds, and then it would be absorbed by the helium-3 gas in the Geiger counters, and the Geiger counter would go click. And so what we are listening for, the Geiger counters have a low background level that clicks, once every few minutes, but what we're listening for is a whole sequential of click, 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 over a few seconds. So it's that 10 seconds of excitement that we are waiting to hear in our Geiger counter. That's the signal of a supernova explosion. So our detector in Sudbury is one of 7 detectors worldwide that are connected to the supernova early warning system. There are 2 neutrino detectors in Japan, 2 in Italy, 1 in China, and 1 at the South Pole. If any one of them gives a neutrino signal, that could be just an error in the electronics or noise or something. But if 2 or more detectors simultaneously report a signal of neutrinos, then a server at Brookhaven National Lab in New York would send out a warning to the international astronomy community, telling the astronomers, get your telescope ready because a supernova just exploded. By the way, you can Google SNEWS and you can get subscribed to receive warnings on your cell phone or by email if you want to know when the next supernova is coming. My colleagues and I are thinking about building something much bigger called Halo 1 kiloton, because there is a kiloton of surplus lead in a lab in Italy, which we can use to build a much bigger version of the detector that we have in Sudbury. So that's the research that I am presently working on. Other people are also thinking big. That group in Japan, which built that huge water tank, want to build an even huger water tank, 10 times bigger, called Hyper-Kamiokande. So you can see, I don't know what superlative they're going to use for one after hyper, but you can see how big that is compared to the old one. Canadian scientists are involved in the design of this neutrino detector as well. There's a group at TRIUMF which is doing research and development on developing more sensitive light detectors to put into this big tank. So here's our Milky Way galaxy. It's about 100,000 light years in diameter. And since a supernova explodes we think about every 30 to 50 years, that means that there are neutrinos from hundreds of supernovae that have already exploded, and neutrinos are already on their way to the Earth. So we're guaranteed that we will have a signal sooner or later. It's just a matter of getting ready to greet these neutrinos when they arrive. And so that's what we're doing. We're building the next generation of neutrino telescope to be ready to observe these neutrinos when they arrive. So as we're waiting, we can ponder about what star is going to turn supernova next. Here's the constellation Orion, the Hunter. That bright red star at the upper left-hand shoulder of Orion is called Betelgeuse. And it's obviously kind of unstable because its brightness fluctuates up and down. And some astronomers think that sometime in the next 50,000 years, Betelgeuse is going to go supernova. So when that happens, it's going to turn so bright that you can see it in broad daylight. In fact, it'll probably be so bright that it'll hurt your eyes to look directly at it. And that will persist for a couple of weeks, and it will slowly decay away, and then there will be nothing there. Orion is not going to look the same anymore after that. It's not going to look much like a hunter anymore, so you can look at that outline and use your imagination. Maybe more like the Canada Goose, huh? So we're going to have to turn the torch over to a younger generation of neutrino astronomers. I hope maybe some of the young people in this audience would take up the challenge, and so I can pass the torch on to you. All those Nobel laureates that I showed you pictures of were all men, but women as well as men are welcome in physics and astronomy. Last fall, we were delighted to learn that Professor Donna Strickland at the University of Waterloo received the 2018 Nobel Prize in Physics for her work on lasers. So Canadians are continuing to have global impact, men as well as women. So this is the second Nobel Prize in Physics for a Canadian in only 4 years. So go Canada, go! So this brings me to the end of my lecture. I hope you have enjoyed my journey into the field of neutrino astronomy. So thank you for listening.
Well, thank you very much, Dan, for that wonderful lecture, and I'm sure you'd be willing to entertain some questions. Yes.
I was curious, how close does a supernova have to be to become dangerous?
Betelgeuse will not be dangerous, and it is, it's 600 light years away. But if Alpha Centauri were to turn supernova, I think that would be dangerous. So somewhere in that range.
Yes?
Just a quick question about logistics with your Halo 1 KT. About what would the shipping cost be of a kiloton of lead coming from Italy going to Sudbury?
It would be tens of millions of dollars, so that's why we're not going to ship the lead to Canada. The lead is already in Italy.
So you're going to help the Italians out?
Yes, so they have given us lab space, and we just have to find money to build this thing.
So if supernova is detected in our galaxy, how much directionality are you going to be able to determine from these detectors to say, look over here?
Okay, that water detector in Japan has a directional capability of a few degrees. So it kind of tells you what direction in the sky to look at. The field of an optical telescope is a fraction of a degree usually. And so it's not quite good enough that you can say, point your telescope at that exact location.
Are you considering the use of helium-3 alternatives for your halo detector?
The alternatives to helium-3 for neutrino detectors?
We explored that. Another type of neutron detector is another substance called boron trifluoride, BF3. That is less sensitive than helium-3. And it would drive up the cost of this neutrino telescope considerably. So we're right now trying to negotiate with the Department of Energy in the US to lend us the helium-3. We couldn't afford to buy it, but those discussions are in an early stage, and if that doesn't work out, then we have to look at alternatives.
What about the heavy water in comparison to regular water allows it to detect the tau and muon neutrinos in addition to the electron neutrinos?
There isn't that much heavy water available, And in the Sudbury Neutrino Observatory, they borrowed $200 million worth of heavy water for some years, and they had to return it all. And the insurance costs were, what, $1 million
Well,
a year?
before 9/11, the insurance costs were negligible. After 9/11, it was a couple million a year. But we gave back all the heavy water, and that's now been sold, and they're not actually manufacturing any heavy water in Canada at the moment. And so there isn't a lot in surplus. We should say that I was in charge of returning the heavy water, and we gave back more than we received. And that's because the federal government didn't really understand propagation of errors.
But the question was, why could it see all three neutrinos instead of just what, say, the dry cleaner?
Okay. Because heavy water has this reaction where if any type of neutrino hits the heavy water, which is just a proton and a neutron stuck together, not very tightly, then any type of neutrino hitting this can release that neutron. It breaks the bond apart, so to say. And so that you can detect that neutron, and that's sensitive to every flavor of neutrino, whereas those other two detectors you need a nuclear transmutation where you change chlorine into argon, for example. And the mu and tau neutrinos can't do that.
How did you know that, or how did they figure out that the neutrinos were changing flavor on the way to the Earth as opposed to being created differently in the sun?
How do you know they were changing along the way rather than just being made in the sun as a different flavor?
I guess you can't absolutely prove that, but that hypothesis is consistent with what we know about how nuclear fusion works. And it's consistent with what we know about other things in nuclear and particle physics.
I could perhaps add that Stan at one point explained that the muon, which is the cousin of the electron, has a mass which is 200 times the mass of the electron. And in nuclear fusion reactions, creating objects of that mass, there just isn't enough energy to create such a big object. And in the normal fusion, if you produced a muon type neutrino, you'd also have to produce a muon because there aren't any muons in the sun initially. And the creation of that extra particle, if you think about E equals mc squared, you create a particle that big, you have to have a source of energy. It's not available in a typical fusion reaction.
Didn't you also mention in one of the slides that it was directional and they could use that to match up this plot in the sky for suns and confirm that way?
Yeah, so what was the question?
Did you mention that there was directional capability for the neutrino detectors?
Yeah, the water detector does have that capability. The HALO does not, and Ray Davis's detector also did not. So you could say with Ray Davis, you don't actually know where those neutrinos are coming from that are making those radioactive argon atoms, but Super-Kamiokande proved that they were coming from the sun.
Oh, yeah.
The electron neutrinos then that decay into the muon neutrinos, since the muon neutrinos you're saying have a higher mass, do they have a different velocity or do they just lose energy?
They do have, it's more complicated than that. What we call an electron or a muon or a tau neutrino is actually a mixture of 2 or 3 different masses. And you can think of neutrino oscillations as analogous to a beat phenomenon in acoustics. You know how you play 2 different sounds that are very close to each other frequencies, like 800 hertz and 801 hertz. If you play each one of them one after the other, you wouldn't be able to distinguish between 800 hertz and 801. And if you play them both together, then you'll hear the beat phenomenon go, oh, oh, oh. and the difference between those two frequencies. And so neutrino oscillations are something like that, where an electron type neutrino actually has two different frequencies in it, which are beating against each other. And so you start with an electron type neutrino of high intensity, the intensity drops after a while and then builds back up again and then drops again. So it's not that electron type neutrinos are decaying into muon and tau type neutrinos. They're continuously changing from one type to another according to this quantum mechanical beat phenomenon.
Sorry, you mentioned the Crab supernova, and it was seen in China and by people in North America. Why is there no record of this phenomenon in European documentation, or has anything been?
Well, that was in the Middle Ages when people were more preoccupied with other things, I guess. That was post the Battle of Hastings, for example.
Yeah. We're busy swarming across from France to England. And it's all covered in cloud in England.
How many years did it take for Ray Davis' experiment to be taken seriously by the physics community?
I would say until the water detectors published their results, nobody really believed it.
I think so. I mean, his experiment ran for 30 years after the results from SNOW came out, which proved that all the work he had done was correct. He got the Nobel Prize that year that our results came out. But it was 30 odd years. Okay, I don't see any more questions, so let's thank Stan again for